Okay, so this is going to be the review video. This program's a little buggy, so bear with me. I have 20 things to go through, and a lot of it is really simple stuff, and I just want to make sure that we hit every detail so we don't miss anything that seems really trivial. So I'm just going to start off with axes, the axes of graphs, and you're going to see them a lot of times shaped like this or shaped like this, where you have x here and you have y here, x here. And I just wanted to point out one little thing, that if you see the graph represented like this, it doesn't necessarily mean the rest of these quadrants are blank. Each of these is called a quadrant, by the way. Yeah, so if you see something like this, it doesn't mean there's no data down here. So for example, if you see something like this, it may be also true that there's a circle hiding everywhere else. So it may look like this when you zoom out. And also, you may see axes of the other quadrants. You may see axes shaped like this, where this is y and this is x. You may see quadrants like this, where this is x and this is y. And what's the last one? Did I miss one? Oh yeah, something like this. So these are the L shapes. The L-shaped type graphs would show each of the only quadrants, and it's basically restricting how much you're seeing of the full picture. And I just wanted to point out that, you know, there could be more hiding behind it if you only see part of the picture. So the next thing is that, so let's say you have a graph like this. I just wanted to point out that a lot of times you see it as y and x to explain to you a function or a graph or something, but it could also be x and y, or it could be, you know, it could be anything you want. It could be q and w, it could be p and l. Yeah, so the letters you pick are arbitrary, so just be aware that these also function with any value, not just y and x. And that'll become important because we probably will be swapping them up at some point. Last thing, oh yeah, it's called two-dimensional because there's only two things here. So if you have just a line like this where the value is x, this is known as one-dimensional because there's only one dimension of values you can take. Whereas this is two-dimensional because for each x value, there's a whole bunch of y values you could also have at the same time. And then this keeps going up to 3 dimensions, although we're not going to do anything in 3 dimensions. So this is like 3D space. This is a little tricky to draw, but that's what a 3D axis looks like. That won't come into play with what we're doing at all. We're not going to be doing 3D things, but I just want you to understand what dimensions mean and why this is called two-dimensional. And the last thing for the axes is being able to read points on a graph. I'm pretty sure you know how to do this, but I just want to make sure that I'm not skipping over anything, assuming you do. So points on a graph may be floating somewhere in here, and each of the points is going to have a point associated with it that looks like that, where this is the x value of the point and this is the y value of the point. So you just pick it like this. Oop, I did that backwards. This is going to be x. This is so messy. Okay, well that's going to be x and that's going to be y. I think you know how to do this anyway, but I'm just pointing out how to find the coordinates of points. That's how you say it, the coordinates of points. And that should be all for graphs. So the next thing is functions, or the word function, and I want to define it for you. So you have heard the word equation, and functions and equations are essentially the same thing, but function is a little bit more of a strict definition, so I kind of want to separate those two and make sure you know the difference between them. Although there's really not much difference. They both point to the same thing, essentially. So an equation is something that has an equal sign. Pretty much anything that has an equal sign is called an equation. So you're going to see something like x squared equals y or something, anything that has an equal sign is called an equation. Whereas a function, this is also considered a function, but when someone calls it a function instead of an equation, they're choosing to do that because they want to emphasize the input and output nature of it, where if you call the x the input, then the y is the output. So it's going to be something like this, where you have the function doing all kinds of stuff inside, and then you have x going in and y coming out. So again, calling it a function doesn't change what it is or how it works at all. It's just that choosing to call it emphasizes how you put one thing in and something else comes out. Now, on the other hand, the function also, calling something a function also does have a strict definition where some equations are not functions. And that's determined by the vertical line test. So if you have a graph something like this, and it squiggles like that, the vertical line test says that at any point in this area, if you draw a vertical line, it will only intersect with the graph at one point, which in this case is this little point right here. So this would be considered a function because it satisfies that. Whereas if you did something like this and drew a circle, if you put a vertical line test right here, you're going to notice it intersects twice, which means that this is not a function, and it fails the vertical line test. So you might also see graphs like this where, I mean, I don't know what in the world would make this shape, but here you could make a vertical line here, and it would intersect once, but here it would intersect more than once. So does this graph satisfy or dissatisfy the vertical line test? Well, right here we see that it fails it because the vertical line test says that for anywhere we put the line, it has to hit only once. So if it intersects multiple times at any point, it automatically fails it, which means that this is not a function. So the reason this should be important to know, because really the only reason I can think of this being important to know is because your calculator can only graph functions. It can graph, it can only graph equations that are functions, and that may not have come up at any point in the past, but one situation where you might see it is if you try to graph a circle. So a circle has an equation something like this. This is the equation of a circle whose radius is 1. So the real graph of a circle like this is going to just look like that. But if you punch it into your calculator, what you're going to get is something like this. It's going to be the top half of the circle. And the reason for that is the real circle is not a function. So the calculator interprets it so as to make it a function. And it does that by just ignoring the bottom half. And you can see this kind of algebraically. If you try to put this into a calculator, you'll have to solve for y because that's how it's shaped. So if you solve for y, it's going to be, it's going to be y equals the square root of 1 minus x squared. Sure hope my handwriting's good. So that's going to be like that. So the problem with this is that for each x value, there can be 2 y values that work. You can see this because if you put in some y value, let's say you put in 5 and then square it, the result is 25, and then you solve for x to be whatever that ends up being. But if you put in -5, square it, it's still going to come out to 25. So because of the squaring, there are 2 y values which end up with the same x value. So going back to this, if we see the x as the input and the y as the output, we're seeing that one x input results in two y outputs instead of just having one output. So we're saying that if we put in x, we don't know which one of these y's is going to come out, really. And when you graph it, it just lists all the possibilities. But your calculator only likes it when there's a predictable outcome. So if you wanted to graph the full circle, you would have to make two equations which account for only half of it. So all of this is not super vital to understand. I think the things you should take away from this are the definition of a function, which is that it has to pass the vertical line test. And you should also know that your calculator can only graph functions. That's mainly important just so you don't get confused when you see something like this. Another example is for the graph of y equals x squared. Let's see. So if I draw y equals x squared, here let me make a new page. Just getting a little cluttered. So if I make a y equals x squared graph, it's going to look similar to this, and that's y equals x squared. So my question to you is, what happens if we turn this into x equals y squared? So if I do x equals y squared, how do I graph this? Well, intuitively, it might not have come to your mind, but intuitively, if we're just swapping the x and the y, it's kind of the same as just swapping these axes. And the result of this is it reflects the graph over this line right here. So you don't have to intuitively know that right now, but it's useful to know that swapping the variables swap the axes, and the result of that is reflecting over this. So more importantly, this tells us that x equals y squared is going to look like this. Now, this, just by looking, you can tell this isn't a function because it doesn't pass the vertical line test. If you draw a vertical line, it's going to intersect more than once. So it cannot be a function. And as a result, if you try to graph this in your calculator, it's going to look like this. It's only going to take the top half, because your calculator automatically has to choose between one of the halves in order to make it into a function so that it can graph it. So it's programmed to be biased towards the positive one, so it only picks the positive one. So again, the total lesson you should get away from this is that the vertical line test tells you whether it's a function or not, and you can only graph something if it is a function. And the reason you need to know that is just so you don't get confused when you're trying to graph something on your calculator. So now I want to describe how to actually graph a function. So if you're just given the equation, how do I make the graph of that function? And as far as I can think of, there's only three ways. The first way is just writing it in your calculator. So putting it in the form of y equals something, and then putting it in your calculator, that's one way to automatically see the graph. And honestly, that's the way I usually do it, just because I've never not been able to. The second way, the second way is by inputting points. So if you have y equals x plus 5, one way you can make the graph is, first by drawing your axes, and then plugging in values of x and seeing what comes out of y. So, so if you put in 1 into x, you're going to get 6 for y. So you just go over to 1 for x and 6 for y and draw a point. And if you put in for 2, you'll end up getting 7 out. So you just go to 2, and you just go to 7, and you just draw another point. And then you go point by point, and the more points you make, the closer it's going to resemble some kind of shape. and then you just draw a line through all the points, and there's your graph. So inputting points is the second way to graph a function. The third way to graph a function is by knowing the shape already, and just knowing the parameters. Parameters is a word meaning, well, I guess I won't use the word parameters, it might confuse you. But one example of this is when I did this to draw a circle. I knew what the circle already looked like because I know what the shape of a circle equation is. A shape of a circle equation is x squared plus y squared equals the radius squared. So the radius squared equals 1. And I just know that this is the shape of a circle equation. So just by looking at this, I can tell what the radius of the circle is. There's also some parts that tell you where the center of the circle is, but I'll just make this a simple case just to show you what I mean about knowing the shape of an equation and then automatically knowing what the graph will look like because you've memorized that equation shape. So the last thing about functions I want to talk about is the notation. When you see functions, a lot of times they're just going to be like, they're just going to be y equals something, but sometimes you're going to see this instead, where you put that little bubble x next to the y. I just want to make sure you know that this is not multiplication. So if I were to do this, yeah, that's the confusing part. If I were to do this, this is multiplication, but this is not multiplication. What this is this is y. This whole thing is y, but this is put here to tell you that it's a function of x, meaning that x is going to be the thing on the other side that takes the input values. And I just want to make sure that you know that this is not multiplication. And a lot of the times, yeah, so y of x is not the same thing as y times x. Ooh, I just realized x and times are the same symbol. You know what I mean, though. So to avoid confusion, if you ever see x and y multiplied together on the right side, they're always going to write it as xy, and you should too. Yeah, they're never going to write y parentheses x when they mean multiply, and you should avoid that as well. So that's an important notation that you should recognize when talking about functions. So now I want to talk about domain and range. I'm pretty sure you know what these are as well, but we want to make sure that you conceptually know them. Let's see. So if you're given a graph like, well, let's just go back to the circle. And let's say this is 1. My numbers are a little ugly. And let's say this is 1 as well. The domain is how far in the x direction the function goes. So in this case, the domain is from -1 to 1. This isn't the right notation, but I'm just making sure you understand. So the domain is how far the function goes in the x direction, and the range is how far it goes in the y direction, which in this case is just coincidentally going to be also -1 to 1. Notice that it's not the distance. So if this distance is what we were concerned with, that would be a range, or that would be a distance of 2. So we're not saying the domain is 2. The domain is telling us what the boundaries are. So in case that we -1, which is over here, and 1, which is over here, the domain is -1 to 1. And the range is basically the same thing in the vertical direction. So you may see functions also which go on forever, like this. They just keep going and going. You would say that since this one in particular goes forever, in the x directions and forever in the y directions. So in this case, you would say the domain is negative infinity to infinity, and the range is also negative infinity to infinity. You may also see things where, so this is very similar to what I just drew. So this one kind of goes like in that direction and in that direction, but this one has an asymptote, and we'll talk about asymptotes in a minute. But the point is that it goes infinitely upward and downward, but it never gets farther than this dotted line. That's what an asymptote is, and we'll go over this in a little bit again. So in this case, the domain would be just this dotted line to this dotted line, so it might be -2 to 2 or something like that. The range, the vertical span of it, will be positive infinity to negative infinity. So hopefully that, okay, so I'll just write it down. Writing is hard. So 2 to 2. This is the wrong notation, but it's easier to write it this way. I think the right notation is brackets. Yeah, this is the right notation. So the domain in this case would be this dot to this dot, which I'm just calling 2, and the range would be, range is going to be negative infinity to infinity. And in this case, you do parentheses because you're not including the points. But most importantly, just the idea of what domain and range are is important, vaguely. It's really just important to be able to measure that value. I don't think you're really going to be tested, like asked what is the domain of this, what is the range of this, but it is an important thing to know how to do. One last thing about domain and ranges. The easiest way to see the domain and range is to look at the graph, and more than looking at the graph, but also understanding how it behaves. For example, these look very similar, so you would actually have to look at the equation to see whether it has an asymptote or not. But I just want to point out that you can't just plug in. So if you have, whoops, there's a random line. Well, if you just have y equals x squared or something, you can't always just plug in. Okay, well, in this case you can, but you can't always just plug in x equals infinity and see what comes out, because let's say the lowest. Okay. So because a lot of times. Okay, so let me just draw x squared like this. So you can plug in negative infinity and infinity to x, and it will give you the max and min values along the y. Okay, so basically I'm just saying I'm basically just saying that you can't always plug in infinity to see what the bounds are, because some of the boundaries of the domain and range may not be all the way out there. They may be right in the center, or they might be at -1 or something. So really just understand the shape of the equation. There's not really an algebraic way of solving it. You just gotta understand how it behaves. So now I'm going to talk about zeros and intercepts. A zero of a function, so let's say you have a function like this, and it goes like that. The zero of a function is whenever y equals 0, which would in this case be right here. So if I asked you what is the zero of this function, your answer would be the x value at which it hits the 0 mark. So it's the x value, oh, this is ugly, but it's the x value at which y equals 0. That's the 0 of the function. And you can get that by plugging in y equals 0 to the function, and you can also get it just by looking at the graph to see how it intercepts that. Now, you could also have a function that goes like this and has multiple zeros, so in that case you would have to give multiple answers to the question, what is the zeros of this function? Let's see. A function could also have no zeros, like in the case of this, where this is the origin, the 0, 0 right here. You see it never really hits the 0 mark, so you would just say there are no zeros for this function. So the 0 that I just described is also known as an x-intercept because it intercepts with the x-axis. So if I were to ask you what are the x-intercepts of this function, you would just give me the same answer. It's wherever it intersects with this x-intercept. Now similarly, there's something called a y-intercept, and that's pretty similar. It's just where it intersects with the y-axis. So in this case, of this function, the x-intercept is here, where the y-intercept is here. And when I told you to get the x-intercept, you just plug in y equals 0. Well, for this, you just plug in x equals 0 to get the y-intercept. And if you think about why that's the case, it should make sense. Because if you just follow this function and you plug in x equals 0 is right here, and so the y value is just this, which is the intercept. We could also find the intercept of two functions with each other. So if I have a graph like this, I could have a graph going here, and I could have a graph going here, and it could intercept there as well. That's a really mess, but the point is there's going to be an intercept here, intercept here, intercept here. And so if I gave you those two functions that look like spider webs, and I asked you what are the intercepts of these two functions, generally, so these are not what those functions are, but I'll give you a couple functions. So if I just gave you two functions and I said what are the intercepts of these functions, what you would do is set y equal to y like this, and so this is constraining it to where their y values are the same. Now you just solve for x, and so that would mean that the x values and the y values are the same simultaneously for both equations. So just set them equal to each other and solve for the x, and now you have the x value of the intercepts. And so for each x value you get out of this, just plug it back into one of these equations and then solve for the y. And so each x you put in here will give you a y, and so that counts as an intercept. And that's basically how you algebraically get the intercepts. You could also start by setting x equal to x, and then you would solve for y, the y values, but that'll just end up giving you the same answer. You just choose whichever way is easiest. So now I want to explain tangent lines. I'm pretty sure you know what these are too, but tangent lines are the first thing that is fundamentally very, very important to calculus, and I want to make sure we have a really good grasp of what they are and how they behave. So if I were to draw a circle like this, I'm not going to draw an axis just for simplicity, but imagine there's an axis going right to the center here. I guess I am drawing an axis now. But if I were to draw a tangent line would be something that skirts the circle and intersects at only one point. So if I were to say, what's the tangent line to the circle at this point? Your answer would be this line right here. So importantly, if we zoom in to this little area right here, what you're going to see is the curve and then the tangent line like that. And it's intersecting right here. Very importantly, what's not happening is it's not doing this. It's not intersecting at 2 points. It is only intersecting at 1 point and 1 point only. And that's kind of the definition of a tangent line. Because if it intersects at 2 points, it is not a tangent line anymore. So a key thing here is that if it is a tangent line, meaning that if it only intersects with 1 point, it can only have this one slope at this point. because any other tilt whatsoever is going to cause it to intersect twice. So tangent lines only have one slope at this point. Now, if I were to ask you what's the tangent line at this point, of course it's going to be a different point, or it's going to be a different slope. But again, this slope is constant for this point. So, okay, so I guess that's the last thing we need to know about tangent lines. You really just need to know what they are conceptually. We are definitely going to play with them a lot in calculus. So the next thing on the list is asymptotes. I already bumped on them a little bit ago, and I think you probably get the idea. We don't really need to calculate asymptotes in calculus, but we do very strongly need to understand them conceptually. So I'll just redefine them again. So an asymptote is, so let's say you have a function like this. Let's say you have a function like this, where it's going on forever, and so this is x and this is y. So let's say it behaves like this, where the farther you go to x, the closer and closer and closer it gets to this dotted line, but it never ever equals the dotted line. That's the definition of an asymptote. It's where the equation approaches a value but never reaches it. Now, this is not to be confused with, well, sometimes you'll visually see an equation that looks like this, and it gets closer and closer, but then like a million years later it eventually crosses. That is not an asymptote. It has to, in order to be an asymptote, it has to forever and ever get closer and never cross. So just be careful when you're graphing something and you see it getting closer and closer. You have to verify for sure that it's going to never cross, so that it will actually be an asymptote. And again, we're not going to be heavily calculating asymptotes. I don't think we'll ever do that. It's just that there is one or two calculus concepts that are similar to asymptotes. So we want to make sure you know what these are. So the next thing is polynomials. Polynomials are also very, very important, because when I told you that calculus is a heavily algebra-based course, the algebra that we're going to be doing is based on polynomials. And that's going to be the main core of the course, so we need to make sure you understand polynomials very well, at least how to do algebra on them. So a polynomial is something of this shape. Let me write it out here. Plus b, x plus c. So the key thing to notice here is that you have x, the variable, and it has different exponents. So in this case, it's just x to the 0, and this is x to the 1. So yeah, this is invisible because it just cancels the 1. But this is the definition of a polynomial, where you have a bunch of x's added together, and each of them has a different exponent, and then out here is constants. So these might be 6, and this might be 2. Maybe this is just 0. So this is what a polynomial shape looks like. And it can go above 2, it can go to 3 and 4, and as high as you want. And I think that these can go negative and stuff, but those are not nearly as important. Although we will bump into them, they don't really change how our answers will turn out. But this is a polynomial, and we're going to be working with polynomials a lot, so it's good to understand. It's good to know what they are when you see them, to recognize that they are a polynomial. So these constant numbers are called coefficients, and they're always going to be positive. Well, they can be positive or negative. They can be fractions. They can be any number you can think of, but they are constants, whereas things like x and things like y are variables, so they change. So again, these are called coefficients because they're a constant value for the polynomial. So like I showed here, the coefficients can be 0, and in that case, then this part would just not be visible, and the whole equation would just be this, if the coefficient is 0. You could also have one of these middle terms be 0, and in which case it would look something like, that's ugly, it would also be something like x to the fourth plus x squared plus 3. So they don't have to go in order. It's just if they're shaped like x's with exponents added together, then it's a polynomial. So the degree of a polynomial, the degree is the highest value here. So this polynomial right here would be considered a fourth degree polynomial. Now, more importantly, if I were to put a 0x to the fifth, so this just becomes 0, obviously, because it's multiplied by 0. But this is still, whole thing is still considered a polynomial. This thing right here. This would still be fourth degree, because you could add zeros forever and ever, but that doesn't change. So that wouldn't be useful to give something a degree if you can just change it at a whim. So the degree is the highest value exponent that has an actual thing, an actual coefficient that isn't 0. So this doesn't change what the degree of the polynomial is. So now I want to go over something called conic sections. You probably vaguely heard of it. So conic sections, C-O-N-I-C, conic sections. This conic sections is a group of functions. There's only 4 of them. There's only 4 functions in the conic section family, and they are the circle, they are the ellipse, which is a stretched out circle, there are the parabola, which is shaped like this. X squared is a parabola. My writing is difficult, but x squared is a parabola. And then there's something called a hyperbola. Hyperbola, which has a shape like this, or it could be also in the alternating quadrants, but it has asymptotes like this. That's called a hyperbola. Now, I just want you to know hyperbola by look if you were to see it. We're almost certainly not going to see hyperbolas anywhere in calculus. In fact, we're probably not going to, we're not going to see ellipses for sure, and we're probably not going to see circles, but there's a chance you'll see circles. I don't think you're going to need the shape, need to memorize the equation for the shape of a circle, which just for reference is, this is the general equation for a circle. X squared plus y squared, and that's a and b, and that's r squared, where a and b tell you, I believe they tell you the center of the circle, like the center point, and r squared is obviously just the radius of the circle. So I'm just casually mentioning that. I really don't think we'll need that. So these 3 conic sections we're not going to need for calculus, really. I made a face. But parabolas are extremely important because they're a polynomial. So in calculus we're going to be doing a lot of algebra on polynomials. And since this is a polynomial, this is going to come up heavily, and it's really important to know a parabola when you see it. Although just offhand, it's important to know these just by look as well. And as a side note, I kind of skipped this. I should have talked about this in polynomials, but just to go over some of the shapes of polynomials. If you see an x squared, it's going to be a parabola, so it's going to look like this, or it's going to look like this. If you see an x cubed, it's going to have 2 humps, so it might be shaped like that, or it might be shaped like that. So it really seems like every time you add an exponent, like for example, if you do x to the 4th, it's going to add another hump. So x to the 4th looks something like that. We're not, but this hump might be so small that it kind of just does this. So just kind of in the back of your mind know that you should be able to identify the cube wiggle and the quadratic wiggle. By the way, squared is called quadratic. And so they kind of tend to do this. This isn't too important. I just thought I'd mention this on the side, that they tend to add bumps the higher you go up. And if you're given something like x to the fourth plus x to the third. Like so, if it's a combination, the highest one is going to really determine the shape of it. So the degree of the polynomial is going to determine which of these shapes it tends to take. Although that's just a loose rule of thumb, it's not necessarily a law. So now I just want to touch on the quadratic formula one more time. Or, well, I haven't touched on it yet, but plus or minus square root of b squared minus 4ac over 2a. So the idea is that if you have an equation, I need an a in there. If you have an equation, shaped like ax squared plus bx plus c. So first of all, this is a polynomial. It's a second degree polynomial, and it's the shape of a parabola, because I told you that second degree polynomials will always be shaped like a parabola, like this, or upside down. So this is a polynomial of second degree. It's the equation of a parabola, and a second degree polynomial is also known as a quadratic. It's called a quadratic equation. And this is called the quadratic formula because it only applies to quadratic things. It only applies to second degree things. So the purpose of this, if you don't already know, is, well, if you're given A, you're given B, you're given C, if you take all these and you plug them into the quadratic formula, what pops out, I don't have an output arrow, what pops out is the zeros. That's the purpose of the quadratic formula. So the two things you really need to know is what the purpose of this is, what the output is, and to memorize the equation itself. Again, I feel like it's really important because it seems to randomly come up in all of math because it's just assumed that everyone knows this equation by heart by now. And so I want to make you memorize it just for safety, but I can't really guarantee it'll actually come up in calculus. And even if it does, you're going to have a calculator, graphing calculator, so you can always solve for the zeros automatically with the calculator. Or you can just plug in y equals 0 and solve for the x's yourself. This is just another way of getting the zeros of a function. So again, like I said before, because a quadratic, meaning a second degree polynomial, is going to have a shape of this, or maybe this, or maybe this. One of these, not all of these. So it could have it could have no zeros, it could have 1 0, or it could have 2 zeros. And this equation is going to tell you which one of those is the case, and it's also going to tell you what the values of them are. So if you have no zeros and you solve this, you're going to result in a square root of a negative. So what's going to happen is this is going to end up being negative, and then you'll have a square root of a negative. And as far as you're concerned, a square root of a negative doesn't exist. So that would tell you that the 0 doesn't exist. So when you tried to solve this, you would get a weird answer that doesn't make sense with the square root of a negative, and you wouldn't know how to solve it. So the conclusion you would come to is there is no good 0 for this. The other case, when you have 1 0, is when this whole bubble becomes 0. So what you have is minus b over 2a plus or minus 0. So the case of that is instead of, okay, well, here, let me go to the double 0 first of all. If you have 2 zeros, you're going to have this value plus or minus this value. So this plus this is going to be 1 0, and then this minus this is going to be the other 0. So that's how you get two answers out of this equation. So if your parabola only has 1 0, what's going to happen is this right-hand side is going to be equal to 0. So the result of this is something plus 0 is just the same thing, and something minus 0 is just the same thing. So you're going to solve for two values, but the values are going to be the same. So like it might be -2 and -2. Like, so they're the same numbers, so you can just conclude that there's only one 0. And that's how the quadratic formula is used to find the zeros of a parabola.